Okay, in this video we'll take a look at the expression operator. It's found under helpers standard expression, and we drop one out there and right away we get this error message, can't parse expression, and two parentheses. This is because our master dynamic is set to edit on the fly is turned off, and so TP is trying to evaluate right away as soon as we drop that operator in there. And of course it's empty, so there's nothing to evaluate, and so it throws an error. Fastest way to get rid of that is just press 1 or type 1 and press enter. And pressing enter is important because that tells the expression operator, hey, this is my function, go ahead and start evaluating it until I change it and press enter again. Okay, so the expression operator, some of the basics, you can add inputs for the different types. There's only two data types that it'll deal with, and those are scalars, and then it gives us the ability to name that scalar right then and there. Avoid common names like X, Y, and Z. Those are best left reserved to the system. As well, you cannot use things like E or TPS or any of the other. Actually, let's go ahead and type an A there. We want to take a look here inside the Max 3ds Max help file. There's a section called Expression Techniques, and it talks all about using expressions, which is about 90% applicable to the expression operator in TP. I say 90% because there are a few functions here, these predefined variables, that you cannot use. It does not evaluate. It'll throw an error if you try to type in things like NT for normalized time. It just doesn't understand it. That's not been programmed into it. But things like pi and E and TPS, those will all evaluate. So we can go ahead and throw E in here, and we're going to need an output for our expression operator. Just go ahead and accept that scalar default. We'll pipe that into a memory node that's got an exposed scalar here, and debug. We'll turn that on. So lo and behold, though, we are not getting a value. That's a little interesting. Maybe we need to connect an actual input. Okay, there we go. So you can see, even though it doesn't matter what our input is, the expression is trying to evaluate that variable E, which of course is, as we see there. As well, you can do TPS, and it'll report the ticks per second, which is a constant in Max. And of course we can also do pi and get the value of pi there. Okay, we'll turn all that off. Okay, so the expression operator, again, we've got the inputs that we can add. We can add scalars, vectors. We'll go ahead and add a vector. We'll just call it V. And let's go ahead and get our debug back turned on. Get that value in there. There's sometimes a problem that we see right here is that if you have two inputs and one of them is not being used, even though we're not really using that A value, our expression operator does not evaluate, and we don't see that input anymore. Let's go ahead and take that out. We'll remove that input V, and we still don't get it. Actually, did we not get that correctly? Remove input, rename, remove. There we go. Okay, so now it goes ahead and it shows pi again for us. This is one of the problems that you need to be aware of with the expression operator, is that if you're not using one of the inputs, your expression operator is not going to evaluate. It's going to have a problem. What you can do is you can actually go ahead and connect something into that input, and then it will go ahead and evaluate. Let's go ahead and do this. Let's just go ahead and show V, and of course this is our vector input. We've got a vector here that is basically up in Z, 1.56 units. So the length of that vector is going to be 1.56. And what we see is that this expression only has one output. It's a scalar. And that scalar then is going to go ahead and tell us, it's going to take that vector, in the expression here, and it's going to go ahead and say, well, it's looking for a scalar output. Let's go ahead and output its length. So it automatically does that distance calculation or the length calculation for you. If you go ahead and modify this further, you'll see that it goes ahead and updates as well. So it will, if you feed a vector in and you only have a scalar value coming out, it will go ahead and give you the length of that vector. You can actually also add an output for vector, and we'll just accept the default name. We'll pipe that into the velocity, and watch what happens now. We've got this float of 0 coming in into the value a, which is not being used, and then the 0.3 of this vector into v. V is in the expression. So what the outputs are actually going to do is it's actually going to output both for us. We can see that right down there. It gives us both the scalar value and the actual vector value for it. We can do quite a few different functions inside the expression operator. All the functions are described in that expression techniques inside the max help file. There's your basic operators here for multiplication, powers, and then we've got a bunch of testing values, and we'll talk about that in a second when we get into the if-then functions. Some vector components, so you can actually access specific components. So if we wanted to take our vector and say, give me the x component, well, it's going to go ahead and look and gives us our x right there of our input. So at 4.44 v.x, and we're actually getting a little bit of an error in there. That is probably due to our number of decimal points. So we're a little shy on decimal points. So So we've got some vector arithmetic. You can use all these functions here on vectors, and that includes things like addition, subtraction, dot products, cross products. We'll talk about those here in just a moment. And then operator precedence tells you kind of the top-down order of when operators are evaluated in your expression. So if you start to get a pretty long expression function that you're trying to evaluate, it's good to know which one is really going to be evaluated first. There's those constants, the section that we do not have access to. Let's get rid of that debug there. Okay, trig functions. So if you want to get the sine, cosine, or arc of any of those, you can do that, as well as the hyperbolic functions. And then we can convert between radians and degrees as well. And if you want to get the highest integer based on a value, let's go ahead and do that. So if oops, accidentally hid that output. Let's do a ceiling of a. So let's go ahead and make a 1.5. So 1.5 coming into this function, ceiling of a, ceiling of 1.55. It's going to go ahead and return 2 for us because that's the highest integer. But if we drop this down below 1, say 0.93, it's going to go ahead and tell us 1. Same kind of thing if you use the floor. So it gives you the largest integer less than or equal to our scalar float value there. So if we do floor of a, it's going to try to evaluate the bottommost value. So this has not reached a full integer above 0 yet, so it's going to go ahead and report 0. Now we're above 1, so it gives us 1, but we haven't quite reached 2, so not until we actually fully reach 2, it's going to go ahead and tell us 2. So these are just some of the basic math functions that you're probably already familiar with. Got a bunch of standard calculations if you want to do natural log, exponential functions, power, square root, etc. Some of the very useful ones in TP are min and max if you're trying to compare two values. Let's go ahead and do one of those. Let's add another input, a scalar called b this time, and this, float, make it a little bit bigger, and let's take the minimum value of a, and just we'll check our syntax here. So it is, and of course now since we switched the application it's trying to evaluate, it's going to give us an error. So a comma b, and press enter. Remember to set that function. What it's going to do then is it's going to go ahead and look at the two values, roughly 2 and 4, and it's going to take the smaller of the two, the minimum of those. But if we were to go ahead and drop our 4 even lower, well then it's going to go ahead and output that scalar there. Let's go ahead and turn off our velocity debug. By the same token, we can go ahead and say, give us the maximum between those two, and no surprise, it's going to go ahead and give us the larger value. Okay, so then we've got the functions, if PQR. So if a test is true or false, if it's true, evaluate Q. If it's false, evaluate R. And then of course there's the vector version of that where you're testing and actually outputting vectors in this case. So you want to test some condition, whatever that condition is. It doesn't have to deal with vectors, but your output will actually end up being a vector. Whereas in your if function here, because it's not a v-if, it's just a regular if, it's going to be dealing in scalar values. So let's go ahead and create one of those. Let's ditch our vector for now. Let's remove that input v. And let's set this value. Oh, 2 is fine and 4. Okay, so creating a function with an expression is one of the most powerful things you'll end up doing, because you can create some very large and complex expression functions to test all kinds of values in there. You can test if it's greater than something or less than another thing, and one after another, so you can kind of string them all together to kind of isolate what you're after. So in this simple case, we'll say if A is greater than B, give me a 1, else give output a 0. And so in this case, we can see that scalar already turned out to be 0. So A must not be greater than B. A is smaller than B. Let's go ahead and check that. A is 2 and B is 4. So once we crank this above 4, well, we end up getting 1 out there because A is larger than B. A being larger than B, so it outputs a 1 for us. Okay, and so that's all pretty straightforward, no surprises there. Let's move our debug up here to get it out of the way a little bit. Where it starts to get interesting is when you need to test multiple values. So we'll go ahead and add another input here. We'll add an input for C. And so C, we'll go ahead and make that 10. And what we're going to do here, let's set A back to 2. So 2, 4, and 10, that'll be fine. So 2, 4, 10. And what we're going to do here is create a little testing function that says, well, if A is smaller than B, if 2 is smaller than 4, then we want to test is value A also smaller than C versus 10. So of course it is, and because we didn't press enter, it did not catch our less than there, so let's go ahead and put that back in. If A is less than B, well then I want to start a new if expression inside this. So I'm going to take out that 1 that we were using. I'm going to add a space just to make it easy to read. And we'll say if, and then parentheses again. And we're going to go ahead and type inside the parentheses here. It's probably a little hard to see, sorry, but so if A is less than B, then test if A is less than C, and if it is, then let's go ahead and output 1. Else, let's go ahead and output 0. Okay, and so that's kind of the end of that little sub-function inside there. If a is less than c, then it's going to output 1, otherwise it's going to output 0. Okay, then we got to step back and say, in our larger function, if a is less than b, well, let's say a is not less than b. So it's going to skip this first phrase or step, and then it's going to go ahead and evaluate the second portion. And it's going to say, oh, well, I'm just going to output 0. So let's go ahead and press enter there and check this. Okay, so in this case, it's going to output 1 because, in fact, yes, a is less than b and a is less than c. But in this case, we'll go ahead and switch this around, and we'll say, hey, if a is less than b, test if a is greater than c, and if a is greater than c, then we'll output a 1, otherwise we'll output 0. And if a is greater than b, then we'll output a 0 via this portion here. Go ahead and press enter to set that function, and of course right now we're going to get 0. Let's see, what do we need to do to get that a little bit. What we want to do is actually get it so that it evaluates true. So a needs to be greater than c. So let's go ahead and make c really small value, maybe down here. And you can see that once we cross that 2 threshold, our debug value switches over. Because remember, our master dynamic edit on the fly is turned off, so TP is evaluating all the time. This is kind of one of the harder things to get used to, I think, in TP, is having edit on the fly turned off actually means that it's evaluating in real time. I think they probably should have named that real time and had you turn it on when you wanted it, but whatever. Okay, and so here you can start to stack these functions really deeply, and we're going to go ahead and one of our favorite habits when doing this is to actually take this, copy that function, go into something like Notepad. And Notepad is a much, actually, you know what, let's use WordPad since it will give us some formatting options. Okay, so here we can see how this breaks down a little better. Remember, the basic of any if function is if, and then parentheses, if our condition is true, then do this, else do this. Okay. Kind of the nice thing about that is that you can end up stacking a lot of those inside of each other. So if a is greater than b, then test if d is greater than e, and if d is greater than e, then if g is greater than h, then return true, else return false. And then this is where you have to really start keeping track of your indentations and which part of the function you're enclosing. So kind of a better way to deal with that. In some ways it's a little more tedious, but it will kind of save you, is to actually add your parentheses as you go. So we know right now with the structure that we have right here, if a is greater than b, then we're going to evaluate this next statement. And if a is not greater than b, then it's going to evaluate this statement here. So we can actually go ahead and have another if in here. And so we're going to add those parentheses right away so that we can make sure that we keep track of how many there are. And so inside this, okay, so let's just say that a is greater than b. We'll go ahead and test if if c is greater than d, then test if, and see if we add those parentheses in there right away, it's going to allow us to evaluate that true portion of that statement. But let's not forget to add the comma and then put our else in there. Of course, you don't actually type else, you just type the statement that you want to have evaluated. So that's kind of the good habit when forming some of these long chains like this. You know, tests within test within test. If condition is true, oops, then do this, else do this, else do this, and then if condition, then this, else this. And you see we've already kind of lost track whether or not there's supposed to be one here at the end. So let's do a little formatting routine. So if C is greater than D, we'll test if all this function is true. Otherwise, okay, so there's the break of that statement. So this is the else portion there. And so that closes out okay. One really good thing that you might want to try doing also is open up MaxScript. And if you drop this in here, you'll be able to, of course, see where those parentheses end. And you can kind of structure your functions a little easier. It'll give you a much better idea of where things need to go, just because it'll show you those parenthesis pairs. Okay, there are some other cool things. In particular, first let's actually talk about length and unit. Unit is a very special function for dealing with vectors. It's going to return the unit vector, which is basically a direction. It's a vector in most programming languages and whatnot, call it a normalized vector. Autodesk, Max, 3ds Max, for whatever reason, call it a unit vector. But it is a normalized vector, and that's just a vector that has a length of 1. So that is very important, because anything denoted as a direction in TP, whether it's a memory input as a direction, where is that, right there? Any direction has a specific length of 1. And anytime you end up doing some vector operations, like in this case we have an expression operator that's got 2 vectors coming in, and we're calculating the cross product, which is the X symbol. So the first vector cross product with the second vector is going to return a new vector for us. In a lot of cases we want to, let's actually go ahead and look at that output first. I was going to say, in a lot of times after any vector operations, it's pretty important, if you want to be dealing with unit vectors, to go ahead and stick a unit vector expression in there to bring that vector result back into a length of 1, if you need it as a direction. If not, then there's no reason to bother. Let's actually, you know what, let's do this too. Let's go ahead and create a new expression, because we actually want to test. Well, there's our error again with, let's go ahead and turn edit on the fly off so we don't have to bother with that. Let's go ahead and add, let's go ahead and just type in 1 again. Let's add a vector v and then a new output. This time it's going to be a scalar. We're going to call that scalar length. And judging from our max help file, we can do a length of v. Let's go ahead and do that. Of course, we could also just output that scalar, and it will go ahead and evaluate the actual length, but we'll go ahead and explicitly call that function. And in this case, we're going to go ahead and take, we've got 2 nodes in our scene, these 2 axis helpers, point 0, or I'm sorry, point 1 and point 2. And we're going to get their directions, their y directions, so they're both kind of pointing straight forward. And we're going to take those directions, we're going to get the cross product of those, and then we're going to, in this case with this expression helper, we're going to get the length of that value. Of course, with they're both pointing the same direction, it's probably going to evaluate, yeah, pretty close to 0 there. So don't be confused. Of course, remember your math, that anytime you see an E dash That's actually an E minus 007. That's telling you that there's 7 additional zeros in front of this value, or basically this number here times, what is it, 10 to the negative 7. So, at least I think that's right. Anyway, just think of it as 7 zeros in front. That's a lot easier. Okay, so that's because these two are pointing the same direction. Let's go ahead and steer one of them off a little bit different direction, and we'll update again. Remember, we're not in real-time mode anymore. We've turned that off. Let's go ahead and turn it on so we actually see that. But now we can see that our scalar, our length of this vector, is actually coming out at 0.65 at 9492. We're going to go ahead then and actually use our unit vector expression function. We'll pipe that into this other expression function, and then we'll go ahead and see what we get. Well, look at that. It turned the unit function, normalized that vector coming out of here, turned it into a length of 1. It is going to have direction. We can see that direction value pointing here. So this is like a really small value in x, a really small value in y, and then a negative value in z. It's a little hard to visualize or just think of that, so let's go ahead and give us something to help with that. I'm going to go ahead and use a position born and show you a fun, easy method of indicating directions. We're going to go ahead and use a pistol shot per call. We're going to set the lifespan to be 0, so that it only evaluates on this one exact frame, this very moment. Speed doesn't really matter, but our critical thing is we want the emission distance to come out about here. And you see by default the position born has a variation in the direction. That's going to be a problem, so let's turn that off. And actually we don't have any inputs yet. Let's go ahead and get that vector coming out of here, out of this cross product operation. And actually we want to put that into the direction input, so let's expose that, put that here. Okay, we don't really need that many of them, but let's go ahead and if we crank up our emission distance, and then we also increase the variation, what you see is that we end up getting this kind of this sampled line appearing. And watch what happens as we change the direction of our pointer. It's just a little, if you're not big on vector math, this is a really great way to kind of try to understand it. We'll put these two kind of close together, and we'll actually go into the transform and set it at 0 so we can start off with a clean slate. You gotta love that debug. So you can see as you rotate that, it's going to flip from one direction to the other. What's happening is the y direction of this second one is crossing over, whereas if it goes to the right, then that cross product is going to point down. So this is kind of a handy way to think of your max script here, your max script in your vector math. If you have our first node here is node 0.1, which is this guy on the left, and 0.2 is here on the right. So if we get their y directions and we do a cross product, remember that's actually going to give us the vector direction that's perpendicular to the two of them. It's kind of like these two vectors create a plane, and then coming out of that plane perpendicular to that surface that they create is this cross product vector. And so if we go ahead and we crank it up, you see that, actually let's go ahead and let's reposition this guy 0.2 onto the origin also. It's a little easier to see now. If I can stop moving my mouse so much. So it's based on these y directions, because those are the two directions that we're calculating the cross product on. And there's another big problem of mine, is that you end up accidentally typing something in the expression operator, and now suddenly it can't evaluate. So you have to be careful with that. Let's get this guy back into a good place. Okay, we've got 0.2. So when the direction 1 is pointing straight forward and direction 2 is pointing down this way, the cross product is going to point up off to the left in this direction. Whereas if point 1 is pointing straight forward and point 2 points up, well, that plane, we've got an evaluation here for the first vector, evaluation here for the second vector. So it's going to be coming out this direction. So this is kind of a good way to help visualize math with TP. And just keep in mind your cross product there. Of course, there's quite a few other things that we can do. You can just get the scalar product between the two, and of course we're going to go ahead and pipe that into the scalar input, and that's going to give us a much different value. What we're looking at here is 0.94, and basically in layman's terms, or simple interpretation, is one vector, the scalar product between one vector and another vector is going to give you how closely they are pointing in the same direction. That's going to be a value from -1 if they're opposite, to 0 if they're perpendicular, to 1 if they're pointing in the same direction. So, there we go again. So you see, as we start to point away, roughly perpendicular there, it's going to, that scalar value is basically approaching 0 as we approach perpendicular, and then as it points in the opposite direction, well, for some reason it looks like I may have lied, but perhaps it is the orientation. No. Okay, well, in this particular case, it's going to point 0. It's actually going to go back to 1 when it's opposite. That's it's news to me. I'll have to look at that one. Okay, well, yeah, it's always fun when those things happen. Let's go ahead and do this, though. There's something else that we can do with the scalar product, and that is if we take the arc cos of that value of vector 1, scalar product of vector 2, press enter. What that will do is that will actually tell us the angle value in between those two vectors. So you see here we approach 90, now we're going to come around to 180, and now we're going to start decreasing and coming back toward 90 again when it's perpendicular on the bottom, until finally we get closer and closer back to 0 where they're perfectly aligned. Okay, so arc cos vector 1, scalar product vector 2 is going to give us the angle in between those two. So that's a pretty handy function when dealing with thinking particles, anytime you need to measure angles between directions. Okay, and last but not least, we found a very nice surprise now in TP4, is that previously in TP3 the special animation function called noise was not working, and what this does is returns a randomly generated position for us as long as we feed in these 3 values. So this is what our function looks like. Let's go ahead and grab that. Oops, I'm going to keep max open here. So we actually have, we're going to go ahead and use this selection here. We'll say, right now, I'm not really sure how it evaluates those, that noise, but go ahead and type it in here. We've got values A, B, and C, so noise A, comma B, comma C. Press enter. And what we'll do is go ahead then and for now we'll go ahead and just take this vector, pipe it into the position born. Let's remove that emission distance variation because we actually want to see where it's going to put them. Let's put our helpers on a separate layer, get rid of them. And let's just say pistol shot per call. And then let's also go ahead and add an iterator to control how many times that expression is evaluated. We'll connect that vector output up here into the our velocity. Oh, you can see it went on for a while there. Let's go ahead and turn off the scalar part. Let's reset this. Step forward one frame, and you can see these are all of the numbers that it generated. Unfortunately, these are all static. So what we may need to do here, it's probably based on the fact that our noise function, anytime we're going to feed the same values in there, the same floats A, B, and C for our noise A, B, and C, it's going to go ahead and return us the same randomized noise. So one thing that we might want to do is use a random value and just say per call, and we'll vary those. And you can see because our Master Dynamics turned add on the fly off, it's trying to evaluate every time we add an operator, and here it gets a little slow sometimes. We'll hook up those randoms. We'll make sure that their random seeds are different. And our iterator is set, well, let's just set that to say 20. So our iterator is going to go ahead then and iterate. It's going to call this expression function 20 times. And the expression operator then is going to go ahead and generate the noise value 20 times based on its inputs. And every time it pulls in an input, it's going to pull in a random number between 0 and 1. And so what we get is this whole array of different values for that random noise. This is interesting though. Look at this. The Y and the Z are always the same. That's not good. Do we? Well, let's try this. Let's make sure that our per call is getting per call. It wouldn't be the first time that a glitch has been discovered. Okay. Well, maybe it's the case that our noise function is not what we expected it to be. Perhaps there's still a problem in there. That would be unfortunate. Or maybe just our iterator needs to be calling our position born. No, that's not it either. So, wow, 2 strikes. Yeah, this is going downhill fast. These things do happen. Okay, well, let's see. Let's zoom in here. We can see, yeah, boy, they are all kind of at the same. Well, that's too bad. I was hoping for a noise function. Well, if you can't do it with the expression operator, you can certainly do it with the TP script operator. And so look on our website. We're going to be releasing one of those here in the near future. Okay, well, just one other thing I wanted to mention while we're in the expression operator is when these things are really useful, or another time when they're really useful, especially when you're dealing with some of those long if-then and you're trying to sort particles based on size or age or whatever, you can use the 1 to x. Let's turn off debug. You can use 1 to x or x to 1. Let's get rid of this stuff here. And whenever you use 1 to x or x to 1, remember what you're dealing with is you're controlling either a certain number of outputs or a certain number of inputs. X to 1 is kind of consolidating those and choosing from those inputs based on the x input integer. So it's 0 base, starting with in 0 up until the maximum number that you have. And so this is one place where the expression operator can do a really good job, because it can actually, you can test certain conditions, and you can tell that x input, hey, I want to use input 1 in this case, or I want to use input 2 or 11, whatever. But of course, in that expression operator, you have to do all your testing. You have to collect your inputs, figure out what your function is going to be, and go ahead and do all that concatenated, nested testing in here in order to finally arrive at that one integer value that you're going to go ahead and feed into the x to 1 or the 1 to x. So with 1 to x, of course, you're still specifying an x input, but that x input then is actually controlling which output gets activated. So if you had a particle. So if you had a particle coming in and you wanted to control which group it was going to go into, you would connect all of these to a bunch of group operators here, pick specific groups that you might want them to go into, and then based on your expression, you could evaluate. Actually, the noise is not a really good case in this instance, but let's actually disconnect him. And maybe it would be the length of something. So if the length is within a certain range, or if you have, say, maybe the ceiling value of that length would output an integer there. Let's actually go ahead and pipe that into the scaler. And let's see, are we still processing our, yep, our unit vector gets calculated. So let's go ahead and take a look at our values. Let's turn off that velocity, we don't need that. And actually let's turn this one off as well. Let's just actually look at the x input itself. So it ends up being 1 there. So it would go ahead and choose output 1, and then it would go ahead and assign that particle coming in. We have particle coming out now because that's the data type that we're dealing with. And it would go ahead and assign that into this specific group. So these X inputs are excellent candidates when you want for using the expression operator. Just one last little note, something I forgot to mention, is that sometimes you'll come into a case where you're not able to kind of nest certain functions together. Let's go ahead and delete our little iterator mess. And the one in particular that we have seen before is that, let's say you wanted to do a function that said if A is greater than B, then give me the degree to radians of A, else give me the radians to degree of B. And unfortunately, you cannot nest. The degree to radian function. There may be others in here. In particular, the standard calculations might be suspect, or the ceiling and floor functions. But for sure, the degree to radian and the radian to degree have problems when they're nested inside. And so what you would end up doing instead is you would probably output either a specific integer here to act as kind of a boolean, and then you would use that boolean then to either calculate the degree to radian or the radian to degree. And of course we have little forget where they are. It's probably under math. Yes, so we just got some little expression operators there under the black boxes. M3D math for degree to radian or radian to degree. So a lot of times you'll end up having to kind of use your outputs to call other expression functions, and then from there you can take that result and maybe need to then feed that into another expression operator to perform some calculation. So you will usually know when that has to happen, of course, because it will end up throwing that error at you. Okay, so this is the expression operator. Very, very handy, and if you like expression operator, definitely check out the TP script operator.